Recording in progress.
All right. Welcome back, everyone. We just had the midterm. It's still going on today. I hope you guys have done it, taken it already. It's due at midnight, but the show must go on. This is on linear regression. This chapter you are not going to be tested on, but the content shows up repeatedly in later lectures. So we kind of need to know at least about it. And so to start it off, I need to fix my camera the way I have it sitting. There we go. Linear regression is about graphs. So graphs, we have an x-axis and a y-axis. And in chapter 1, we learned about different types of variables, explanatory and response variables. The x-axis is the explanatory variable when we're doing statistics usually. And the y-axis is the response variable. And so what this is called the Cartesian coordinate system. Usually we have a line on here. And this line can tend to be written in a couple ways. Y equals mx plus b is a common way, and then another way is ax plus by equals c, where in both of these, the y and the x or x and y are variables that change, but the other letters are constant. Other letters represent constants or fixed numbers. Give you a second to write that down. We'll talk some more about y equals mx plus b, and we'll talk about the other one, the standard form. Y equals mx plus b is called the slope-intercept form. Because the m is the slope and the intercept is the y-intercept. Which is, let's see, what color do I want to use? Right here. That's the y-intercept, and its value is 0b, where b is this b over here. So on the graphs, going to the right is positive for x. This is positive x. And going to the left is negative x. Going up is positive y. And going down is negative y. So we can represent all the positive and negative numbers for x and y on a graph. And we list any given point on there as a coordinate x, y. This point right here, I can figure out what it is by comparing it or counting over. I have gone over 1, 2, 3 lines. That's my x value, 3. And I went up 1 line, so my y value is 1. This is pretty handy because we can use it for the slope. So if I do 2 different points on the line, and I do that counting thing, how many times I go over and how many times I go up, the steps to the right are called the run, and the steps up are called rise. How much does the graph rise versus how much does the graph run? M is rise over run. So the line I drew, this green line, has it runs 2 steps, it goes to the right 2, and it goes up 1. So M, the slope, is 1/2. I know by the picture my B is at 0, 1. My Y-intercept. So that value is my B. So I can write that green line as Y equals M, which is 1/2, X plus 1. There's another way of looking at M that you might find helpful, and they reference it a lot in the homework problems in this. So M, or the slope, every time X increases by 1, Y increases by M. In fact, I'm sure there will be problems that ask you, what does the slope mean? And they'll give you something like, every time X increases by 1, Y increases by blank, and they'll ask you to put in what that is. So this is kind of similar to stuff you might see in the homework on this section. Give you another 30 seconds with that, and then I'll take it away and we'll put up another one. This is just some basic reminders about how graphs work, because a lot of this is done with graphing. So if you've taken algebra courses, this is in algebra. All right, if you need that up longer, let me know. Otherwise, I'm taking it away in a couple seconds. All right. If I need to bring it back, I can. I got it set to the side. So I said that we could write a line in two ways. We could do y equals mx plus b, which is helpful to read, helpful to graph too, which is helpful for graphing. The other form is ax plus by equals c. And a, b, and c are numbers. For example, and they don't have to be positive. I could have 3x minus 2y equals 4. So here a equals 3, b equals -2, and c equals 4. I can make ax plus by equals c look like y equals mx plus b. So how do I make this into y equals mx plus b? So the first thing I'm going to do is I'm going to, when I have equal signs, the sides need to stay equal no matter what I do. So I want the equal sign to stay. If I want to make it look like y was mx plus b, I need to get y by itself. So the first thing we do is we move anything that's being added or subtracted to y. In this case, the 3x is being added to it because it's positive. So I can subtract 3x from both sides. And everything else just comes down. The equal sign comes down. -2y comes down. The 4 comes down. And now I've just got -3x over there. And I've got 0x over here. And when we have 0 something, we don't even need to mention it. This is the same thing as -3x plus 4. So I can change the order of these. But I want to get y by itself, and right now it's multiplied by -2. So to get rid of multiplication, we do division. And again, whatever I do to one side, I have to do to another because I want the equality to stay the same. So if I do divide the left side by -2, I need to divide the right side by -2, which means I can divide each individual thing by -2 on the right side. But if I do it on one thing, I got to do it on everything, on every side of every equation. -2's, they cancel each other out and they leave behind a 1. Like 5 over 5 is 1. So that'll leave a y on the left side. 4 divided by -2 is -2. And -3 divided by -2, I can't really simplify that other than I've got two negatives. I can make two negatives into a positive, and I can write this as 3/2 x. And just like I was saying, I can change the order here for this line up here. I can change this order right here. I can say this is 3x minus, or 3/2 x minus 2. And now this makes this easy to graph. I know I need my y-axis to go down at least 2. I guess I didn't need to make so much room here. I go down -2 to match this. That's my y-intercept. So that goes down here. And the 3/2 tells me how much to rise over run. Rise 3, run 2. I think it might be a little bit easier to show the run 2 first, and then rise 3. So if I have the y-intercept there, and I go right 2 and up 3, I have another point there, and I can connect the dots and make a straight line. That 3/2 continues to happen. I could go right 2 more and up 3 more, and I hit the line again. And just like 3/2 started as -3 over -2, I could treat this as going down 3 and left 2. So doing both negatives, which means going, left 2 and then down 3. And that gets me back on the graph again. So that's how the slope works, and the y-intercept work. They're going to come in handy when we're looking at stuff that they give us, which is what we're about to get into. That's just all review. I hope that you guys, it's familiar to everybody. If it's been a while, hopefully this is a good little refresher. I'll leave that up for another second. You guys are writing it down while I clean the old slide. Okay, you guys ready for some more? If you need that up, let me know. So, if we've got data in a table on StatCrunch, we've got 2 columns, and we label them X and Y. We can do a scatter plot. So we've got like X, Y, and it might be like -2 and 1, and we've got like -1 and 3 or 2, and we've got 0 and it's 3, and we've got 1 and it's 2 again, and we got 2 and it's 6. Let's say if I plotted these real quick by hand, I don't need so much downward. I do need more upward though. I got Y as 6 there. Trying to make those as evenly spaced as possible. Now these dots clearly don't make a straight line. So what we will do in this section is look for the line of best fit. Like, how can I draw a line so that when I'm done, the dots are as close to the line as possible? Some might be spot on, some might be off. This is probably not a good line. A better line might be the one. These three are all in a row, and they come close to hitting that other one. But this one's way off. So, like, how do we pick the best line? To fit the data. That's what line of best fit means. And in StatCrunch, this is called a scatter plot. Which we will do in just a second. In fact, I'll even use those numbers I typed there. I'll have to add them in and show you a better looking graph than what I hand drew. You guys need that up longer? Okay, if you do, let me know. I'll put it back. I'm going to put up StatCrunch for a second. I'm going to actually, what I did here is I did view data sets from your textbook. I'm going to do an example with the 4-2 number 7 in a second. But right now I'm just going to use new rows to do the X and the Y I have on. Let's see if I can. So I copied my table over here that I have here. And so we're going to do what I had said. Let's do a graph and a scatter plot. It asks us where the X variable is and where the Y variable is. If you do what I did, where you named it X and Y, it's easy to find. Otherwise, you have to look at the individual problem and go from there. So again, graph scatter plot. I labeled it X, so I'm going to use X. And I labeled that Y, so I'm going to use Y. And we can see, like, it doesn't make a perfect line. I wonder if I can annotate and do a straight line over this with annotate. I can. There you go. So if I drew the line through the first three dots, this one right here, the one on the right, is up too high. This one's too low. I could do something where maybe I have, change the color real quick. Something where goes a little more like that. I just don't know what the line of best fit is, so we've got some tools for that. And I will show you what they are real quick before we go into usefulness. Undo, turn that off. I don't need annotate on anymore. Is it something I can edit and scatter plot that will do it? Oh, I can. I can say overlay a polynomial order and do 1, and it'll give me best fit as an option. Or I can type in values myself. Notice they've got it written this way. I could do, that looks like the M for MX, and that looks like the B. So if I wanted to put values in, I could. I'm not going to do that. I'm just going to say, let's use the best fit and see what happens. And the line was actually lower. So they went lower than the dots. They kept about the same angle. This kind of brought it closer to this one down here, right? It brought it closer to that dot. Let me change the numbers a little bit and do something a little bit different. And I'll recompute because I want to show what's going on here. The way they figure out the best fit, and I'll go through this on equations in a second, but I think showing it pictorially helps. What they're doing is they're finding this vertical distance right here between the dot and the line. So if I call that A and this is B, these are distances, and that's C and that's D and that's E. What they do is they want to find A, B, C, D, and E such that A squared plus B squared plus C squared plus D squared plus E squared is as small as possible. Is the smallest value it can be. And the computer went and figured that out all on its own. It tried a whole bunch of different lines. Well, no, not really. It used some equations to find it. Some math calculations, which I'll tell you what the equations are. We're never going to calculate them ourselves, but it's worth seeing how they do it to understand what's going on. There's other ways to get this line of best fit. I'll show them to you in a second. But I got a little bit more I need to do on the stuff over here to like back up with what we're doing. Because I showed a straight line on this graph, right? Actually, I can do it here. I did a straight line, but what if it followed something like a parabola, where it's curved, or a cubic function? Some data fits really well with cubic functions, or parabola functions. Let me change the values here and give you an example. If I show this with a parabola too, my dots are right on the line. So a straight line here would be terrible. If I do a straight line on this set of data, that looks terrible. It's not reflective at all, when we saw clearly that this graph was spot on. It nailed it. So how do they decide when can we use a line and when do we require something different? Because a line is really handy. It means a direct relationship between one variable and the other. So let's take a look at the ways we have these dots come together. So I could have dots that slowly increase as you go to the right, and dots that slowly decrease as we go to the right. Increase or decrease. And remember, this axis is X and this axis is Y. When we can make the dots make something look like a straight line, we call this linear correlation. Between X and Y. The one where it goes up as it goes from left to right is called positive linear correlation. And this one is called negative linear correlation. We could also have graphs where, like I showed you, we had, something that looked like a polynomial of a different magnitude. This is a parabola. I could have dots that are doing something like this. And the line is doing something like that. Rather than naming each type of graph, these are just called nonlinear correlation. And that can be a lot to remember. But something you might find handy is the one that's called linear has the word line in it. And these make straight lines. Straight lines. And these do not. So they do not make straight lines. No line. And correlation's got the word relation. It's the relationship between X and Y. That should be an and symbol. Ampersand. There we go. That's what it's called, right? And we could have a graph that just looks like this. where there is no relationship or no correlations. I can't make a line that looks good for any of it. The data's just all over the place. Tell me when you're ready for more. I'll be erasing the board for a second. Okay, so how do they decide whether they can use a line or not? Can we use a line or not? Linear correlation or not? So I'm going to show you what they calculate, and then we're never going to use this formula again. Hopefully there's nothing in the set homework that has you do it. R, which is called the correlation coefficient, that's R. It is the sum of, and I have to look at my notes because I don't remember this one. We do x minus x bar over sx times y minus y bar over sy, all divided by n minus 1. The x bar and y bar are the means for x and y. The sx and sy is the standard deviation for x and y. And n is the sample size. N is the number of points. God, no, we do not want to do that. Stats, summary stats, correlation. We will also see another spot where this comes up. Stats, regression, and is it simple? Yeah. Simple linear. The second one's got a lot of info on it. If you only need the correlation statistic, it can be a little distracting to find. What we will need for problems is we will need to know how to get the correlation coefficient. We need to find R using StatCrunch preferably. And we need N to use the critical value tables, which I will show you in a second. Most problems that have you do this, load up the critical value tables right in the problem so you can look for them there. I'm going to come back over here and change these back to what I had before. Shit, I didn't write them down. I had 1, 2, 3, 2, and 6. So I'm going to do that summary stats here for what I got. I will tell it X and Y is where we're looking. And I will just click compute. So for the 5 numbers I came up with, it gave me a correlation coefficient of, I need to unhighlight it to not, the blue is distracting me. I may not have enough points, but we'll find out in a second. Okay, you guys ready for more? Okay, so critical value tables. Where can I find the critical value tables? In your course, you can click on Files. You can click on Useful Handouts. So I'll write this on this slide in a second, but I'm just showing you for now. We're going to click on Stats, and then Stats, Formulas, and Tables. So let me write it down real quick while I got the path up on my screen. Okay. So Files, Useful Handouts, Stats. We want Stats, Formulas, and Tables. And it's quite a few pages down. We're looking for our table. There we go, tables. Table 2 says, it's on page 5 apparently. Table 2 says critical values for correlation coefficient. And notice they use a CV on the table. It's a common abbreviation for critical values. We need to know what n was in our problem. How many dots did we have? And we can come over here and from this table, write down the critical value. So we had 5 dots. This is 0.0. So n equals 5. I've got CV is 0.878. And R, I'm going to rewrite on this page, was 0.834. So that's where we'll find them. And like when you're doing it in the homework, it should give it to you, including later sections, hopefully. Where was I? That's what I wanted. Okay, so what do we do with R and the critical value? We're going to use the absolute value of R. Absolute value of R means just make R positive. So if it's negative, just make it positive. And what we're going to do is we're going to compare the absolute value of R. We're going to compare it to the CV. If the absolute value of R is greater than the CV, a linear correlation exists. And at that point, if R is positive, it's a positive linear correlation. And if R is negative or less than 0, that might be a better way of saying it. R is greater than 0, R is less than 0. We have a negative linear correlation. So I'm going to do that with our numbers right here. Let's just compare them real quick, see what happens. I've got 0.834 and 0.878. In the problem, the numbers I just put in, this is less than. When we have a less than, if absolute value of R is less than CV, no linear relationship exists. Maybe a nonlinear one, though. I'm going to see if I can show. Oh, shit. Lower that down. I'm going to go over here and edit those things again. I'm going to go back to the parabolic one. So for these values, the correlation between x and y is 0. But we saw when we did the graph here, there is a perfect fit. So here, my correlation here is 0. That's definitely below the 0.878. So it says that no linear relationship exists, but there might be a nonlinear relationship. Like this one has a nonlinear relationship. So don't just assume that there's no relationship based on what you get. So there's a lot going on with this R. I think I need to give you a little bit more about it. And we'll do that on the next page. Give you guys a second to write that stuff down. Okay. So this correlation coefficient R, what do we need to know about it? So it's got some properties. R is always between -1 and +1. The closer it is to -1, the stronger the evidence of a negative linear relationship. And I could literally repeat this and say closer to +1, positive linear relationship. As we saw, when R is close to 0, there is no linear relationship, but maybe a nonlinear one. Other fun facts. R is unitless. A lot of the things we're doing, we have units, like 10 feet or 5 seconds or something like that. Feet and seconds is a type of unit. R is unitless. It's just a number. And R is not resistant to outliers. We, or the computer does, we use the mean and the standard deviations to calculate it, and neither of those is resistant. And since neither is resistant, R is not resistant either. which means if we're looking at income and Bill Gates walks in or Elon Musk walks in, they will have a huge impact on R. Those are the fun facts about R. How do we use this? What kind of problems are we going to see? Give me a second to finish writing that. Someone's blowing up my phone. Okay, you guys ready? So for the next problem, I went to StatCrunch and I did it, or Math Lab. Went to my Math Lab, clicked on the StatCrunch tab, and it said use data sets from the textbook. And so if you want to load this up on your own, you can. This is 4.2, problem 7. And I'll show you how to do that. So in StatCrunch, you click on view the data sets from your stuff. Click on chapter 4. Find 4.2, problem 7. And we'll load it up. So what has it got here? It's got 2 columns. Total length in centimeters. And weight in kilograms. This problem is about bears. This is about bears. I don't remember which type of bear, but it's about bears. And is there a relationship between length and weight? And maybe I should be more specific. Is there a linear relationship between length and weight? So while you're writing that, we'll do a look at the scatter plot. The dots are kind of all over the place, aren't they? And I can see by the number of rows. They're going to make that a little bit narrower. I can see by the number of rows that there's 12 rows, so there's 12 points. So we need to see if there's a linear relationship. We need to find R and the critical value. So let's do that. We can find R doing stats, summary stats, and correlation. And then we do to find the critical value, we got to go to that useful handout. In files. And I'll just do 4 decimal places. Appropriately rounded. I probably don't even need that. I think the critical value table only used 3. So maybe I'll use 3. Yeah, I'll use 4 because we can see if it's spot on. I want to know if it's a little bit higher or lower. I'm also going to come over to our table over here. Look at the file. Oh, we're looking for n equals 12 right there. I can see it right there, n equals 12. Maybe I can zoom in a little bit closer so you can see it a little bit better, maybe. 0.576. Yeah. Back to StatCrunch Nally. What I'm doing is in fact, I wrote it down here. Stats, summary stats, correlation. I select both rows or columns and just click compute. There is another way to get this, and I'm about to show it. We can also do stats, regression, simple linear. But I will wait to let you guys finish writing that stuff down before we do it. I hear my wife out there talking to Lunar. She's still deciding if she's going to fall in love yet or not. I know she is. She's being stubborn. My wife worries a little bit that loving the new puppy is betraying the old dog. I know she does. And it's not. All right, you guys ready for some more? I'm gonna have to start cleaning whiteboards here. So stats, regression, simple linear. Okay. So when you click on it, it gives you a lot of information. But we still got to tell it where X is and where Y is. Don't worry about this other stuff for now. Just click compute. First thing to note, it gives me R right here. We had 0.7039, right? It gives me R. It even says the intercept and the slope. They've got written up here, weight kilogram equals this line right here. So we're looking, there's a better way to do this. I can use the zooms feature and just point at the line. So they've got weight equals negative 142.47 plus 1.69. I'm just doing a couple decimal places on these. And then the length. And they've got listed up here, dependent variable is weight. That's Y. The independent variable is X. So what this really says is Y equals negative 142.47 plus 1.69x in terms of graphing. And if we wanted to write it like that, Y equals mx plus b, oh yes, there must have been a reason why Mr. Jones was going over that earlier. My slope and my Y-intercept. And check it out. There's another tab here. We click the tab, and it shows us this graph. It's the same graph, and it shows us this line. That's the best fit line. So this line right here is the line of best fit. You might wonder how they got these. The book or the program will use B1 for this. They call it B1. Maybe I'll put the B1 in front. what they do to calculate it is they find that R value that we had, and then they multiply it by the standard deviation of Y divided by the standard deviation of X. And B0, they just find using algebra, regular algebra stuff. So we're not going to find M on our own. We can always do this stats, regression, simple linear. Okay. And remember, I told you with the ones I did earlier, the way they're finding this is they are doing the vertical distance between these points and the line, and they're trying to find the line that has the minimum value on this. So these are called the residuals. That distance there, are called the residuals. Why am I doing it over there? I got a whiteboard. Quit being silly, Mr. Jones. The residuals, they do. They'll mention this in the staff. It's called Y minus Y hat. Observed minus predicted. So observed is my Y. Predicted is Y hat. Observed means it comes from the data points. The actual dots over here on the map. The predicted is the Y value on the line for that X. So all of these dots up here, the dots are above the line. The residuals will be positive up here. And below the line, the residuals are negative down here. I'm trying to write with the mouse. That's not working that well. And so what they do is they do this, they find this Y minus Y hat, and the line minimizes or finds the smallest value of Y minus Y hat. They square it and they add them up. So this is called the sum of squared residuals. Another word for residual is like error. That's the error. How much is the line off from the actual point? So in StatCrunch, you'll see SSE, sum of squared errors. And I believe it's on the screen right before this. I think it's this SS with the error. Sum of squared errors. Not really all that exciting for you. So for the bears, we had R was 0.7039. And we had, let me annotate again. There's my R. And we had CV was 0.576 from the table. So R is greater than that. R is greater than the critical value. So there is a linear correlation. Pause while you write stuff down, get some more whiteboards clear. Guys ready for some more? Okay, so this showed linear correlation. There is a linear correlation between the length of a bear and its weight. It's important to remember correlation does not mean causation. Causation is where one causes the other. One doesn't cause the other, or may not cause the other. So different things could cause the bear to weigh more. Maybe it's got bigger bone density. Maybe it's got a lot more muscle than fat on it. Maybe the diet is different. So length doesn't necessarily cause weight. You could have a skinny but long bear, and you can have a fat but short bear. Okay. Something else to take a note of. This graph did something terrible. See how the graph starts at 60 and 120? Let's see. They've got a dot at 60 and 120, which is 120 is about here and it's about there maybe. And the biggest dot is over at 160 and about 150. So maybe up there. And there's other dots in here. And they've got a red line showing. That red line was 0.47, which means I need a longer y-axis over here. Negative 142 is way down here. If these are all increments of 50. They had something like that. We see this line over here. The equation gives us information over here. This points out something very important. Recall, this is length, and this is weight. Let's draw that line. I'll use a dash line for stuff. Oh no, I'll use a different color line for stuff they didn't draw. It's like this. So this formula, this equation, predicts the weight of bears based on length. What about a 50-centimeter bear? A baby bear. That's it. That's it. There's bears that are 50 centimeters. That's a half a meter. It's, you know, a foot and a half long. It's a baby bear. Very baby bear. This formula would predict a negative weight. In fact, we can see what it is if we plug it in right here. The formula predicts 1.69 times 50 minus 142.47. I'll get out my calculator. A 50-centimeter bear has a weight of negative 57.97 kilograms. Is that possible? Can a bear have can anything have a negative weight? No, it's not possible. So, this gives us some insight into what to expect. These equations, let me see where I want to write this. Equation is only good for x values in the same range. So we had like 120. You can see it over here on the left. Let me annotate again. We got 120 right there. We got maybe 165 right here. We might be able to do values between, we can go a little bit outside the range, maybe 100 to 180. But you start getting too far outside the range, the equation stops working. So you got to keep that in mind. Ready for a little bit more? I think I only got one more page after this. I do. We're making good time. I'm not done with the page I'm on, but we're making good time. Okay. So some things to know for the problems that you're going to be looking at. I'm going to rewrite the equation of the line real quick. Remember, we got it from stats, regression, simple linear. And notice these values right here are also the values down here. It might just be easier to pull it from this. Y equals 1.69x minus 142.47. So they will ask you things like this. What does the slope mean? They might call it B1 or it's the M. Either way, it's the 1.69. And it means for if x increases by 1 and x is the length, by 1, in this case it's in centimeters, then y, which is the weight, increases by 1.69 and the weight was in kilograms. So they might ask you stuff like that. And more importantly, this is the average increase. It's only a true increase in y if they're all a straight line. So maybe a better way to say this, increases by an average of 1.69 kilograms. Other things to take note of that they should ask you about. Does the Y-intercept mean anything? In our problem, it's the negative 142.47. And this is the kind of the rule that you want to live by. 1. Are there any values, x values, I should say, any x values close to 0? That way, like, are we in the right range? This 120 to 165 was not. But if we were looking at something and it had like 0.5 to 3, well, 0 is pretty close to it, and so that's reasonable. The other thing you want to look at, and it's only if the first one is true, if so, does x equal 0 make reasonable sense? For the problem we were looking at, x was the length of a bear. Does x equal 0 make sense? If either of those is no, a no answer, don't interpret the Y-intercept. It doesn't make any sense to you. So in this problem, we can't have a bear that's a length of 0. That would be a non-existent bear. So interpreting the Y-intercept for this graph doesn't make sense. If it does make sense for whatever you're doing it on, then you can use it for its correct interpretation, and it would relate to whatever the y-axis is. In this case, kilograms. So we would interpret it as whatever the y-intercept is in kilograms. In our problem, though, we didn't have that. Ready for some more? Problems you'll see in this section. I'm going to relate it back to the bear again. So we got the data set up on the screen still. Typical question. For the homework, it would be like, if we had a bear And let's say that the bear is 160 centimeters. If we had a 160 centimeter long bear weighing 139 kilograms, is the bear heavier or lighter than the average bear of the same length, of similar lengths? I'll give you a bit to write that down. There's a lot there to unpack. Okay, so we had the equation y equals 1.69x minus 142.47. This is the average bear. So let's figure out what an average bear would weigh of that length. We're going to plug in the 160 centimeters. And I'm getting y equals 127.93, and that's kilograms. That's the average bear. Our bear was 139, so he's heavier. Pictorially on the graph, what that means is the average bear is along this line, and we had like 160 right here. The average bear is right here at 120. Let's just use whole numbers, 128. And our bear was a little bit higher at 139. So he's above the line. He weighs more. But notice you have to plug the value into the equation. To find the average bear's weight. Okay, one more section. This is actually not in chapter 4. This is in 7.3, but it required you to know about stuff in chapter 4 to make sense. 7.3 was on assessing normality. Remember, chapter 7 was on the normal probability or normal distribution. So this section is entitled Assessing Normality. Is a data set normal? So some things to know. A normal probability plot uses observed values for x and z-scores for y. Ah, shit. Trying to move the zoom window. Okay, so oftentimes we only have a single column to look at. So often only a single column for data. So I can't use that QQ plot or I can't use the scatter plot or the simple regression or anything like that. There's often only a single column to look at. So we have a couple options. If it's the z-scores, we should be able to do stats, regression, simple linear, and just select that single column. Usually it's not though. Usually it's just the observed values like I have on the screen here. And for that, we want to do something called the QQ plot. You want to, when you're doing it, and you'll see it when I do it right here, add correlation stat. You want to do that. And we want to do normal quantiles on y-axis. So the problem I brought up, this is like similar to the chocolate chips problem we were doing in chapter 7. This is actually the data for it. So what I'm going to do here is, since it's the actual data, I'm going to do the QQ plot. add correlation statistic, and do normal quantiles on the y-axis. So this is the StatCrunch thing right here. Graph QQ plot. I've checked the correlation statistic. I've checkmarked the normal quantiles on y-axis. And it gives us a value. And we can kind of see the dots kind of follow the line, right? Gives me a correlation of 0.986, which is really close to 1. But we still got to go through our normal thing. We got to go find the critical value. And notice we have another table down here. Shit. I zoomed out. What the hell? Critical values for normal probability plots. So table 6. The largest it goes up to is 30. So we're going to use the n equals 30. The n equals 30 value is 0.960. That's n equals 30. That's the max. Our correlation value is still higher than it. Move this to the left. Our correlation is still bigger than the critical value, so there is a linear correlation. And when we see the picture in, we look at that and you'd go like, looking at it, yeah, those dots are all pretty much in a line. You can easily see, looking at it, that there is a linear correlation. So, what that tells us when we're doing a normal probability plot I only got one line left. I'll just write it here. If this stuff is true, ignoring the chocolate chips, we already showed that it's true. Ignoring the chocolate chips, if the R is greater than the CV, the data is normally distributed. Wow. I just skipped words that I was saying. Let's do it right. So sometimes we want to do that. In later we will look at QQ plots to check. Can we assume this data is normally distributed? That's pretty important for chapters 8 onward. Everything we're going to do after today, we want our data to be normally distributed. And if the problem doesn't tell us so, or we don't know that it's normally distributed already, we kind of want to check this. So we want to make sure our data is normally distributed. This is how we do it. And we're doing the correlation statistic. This is on the QQ plot. Right there. And we find the critical value in that table in the useful handouts. And other than that, we're done for today. Oh, look at that, 8:28. Do I know how to time some shit right? How about that? Thursdays might be as long. I don't think it's going to take 2 hours. Many of the sections from here on are not going to take 2 hours. But I don't want to like do 2 hours worth of lecture stuff and overload you. I thought we'd get this all knocked out in one lecture though, because we'll see this stuff again on the actual final. You'll be able to assume stuff is normally distributed and stuff like that. I'm gonna tell you that assumption is valued, so that we don't need to do any of this. The final is also not in StatCrunch or MATLAB. It will be in Canvas, and I will give you all the StatCrunch values. Inevitably, there will be 10% of the students that go through and put everything I put in and try to recalculate their own values. And sometimes they get the same thing I do, which means they did it correctly. Oop, I see chats. Cumulative only in that the idea we're not going to have like you don't need to do probability of E or F equals probability of E plus F. There's like, it's not cumulative in that sense, but the stuff we've worked on does kind of trickle in. The idea of unusual being less than 5%. The idea of how probability works in general, not the formulas. We're not using the formulas again. Yeah, there will be a practice final when we get there. But I will give you everything from StatCrunch. You do not need to verify it. I will have gone and done it in StatCrunch myself. Usually the people that went and verified it themselves have not paid attention to a goddamn thing I've said in any of the videos, didn't attend lectures, and generally did bad on the final anyways. So I kind of know right away when someone does it that they're likely not going to do well because they haven't been listening. But you guys won't be part of that because you guys show up every day. Any other questions? People are bouncing. All right. I will see you guys later.